Welcome to ViViMaT. This is the second Q&A session where we'll discuss the presentations and favorite ice cream flavors of Ingrid Padilla Espinosa and Manel Rodríguez Ripoll. Codings is a peer-reviewed journal of codings and surface engineering published online by MDPI on a monthly basis.
Okay, so hi everyone. I think some of you already know me for a couple of years. Others, have not seen me before because Stefan was more active, especially with the kids, presenting very nice talks. So first of all, welcome to the second Q&A event of the ViViMaT channel. It's a pleasure to have you almost all online now. There's just one colleague missing. He may join us a little bit later. So first of all, thanks to Stefan for doing really excellent job in setting up the whole story and nicely presenting it, and of course to all the presenters with fascinating topics, I must admit. Also the second round, when I had another quick look again this afternoon, I was really impressed by all of the work. And I'm very glad that you found the time and, of course, the will to participate in our small round. So for today, I wouldn't go for too strict procedure. So last time we also tried to make it a little bit more easygoing. I think also for today, it will not only deal with questions related to your presentations, maybe also to give an outlook of your work for the future, and also maybe in the very end of the Q&A event for today, discussing a bit of your experience with these kind of platforms that most of the time, of course, popped up during the COVID situation. I know the pros and cons. I just would like to hear some feedback from your side. How is your experience with that, and where do you see any kind of improvements in the future? And as I said, also maybe to have a comment from you about your future work. What are you interested in, and what are you currently actually working on? So we have a couple of questions. Some were left on the web page or on the YouTube channel directly, and others have been collected from colleagues and Stefan and myself. So now the question is, Stefan, do you wish to start with some questions, or shall I start? What do you prefer?
You know, I have a suggestion. Since Ingrid is the one who actually got up at the crack of dawn, how about we make it worth her while and just give her the first one or two questions so that at least she can say she got up for a good reason. That makes sense.
That sounds like a good plan, yeah.
Also, well, I'll say I'm still at the East Coast. I haven't been able to go to California yet. I'm sorry, I should have communicated that earlier. It's 10 a.m. here.
Okay, so I wasn't sure. So you're North Carolina. You're North Carolina?
Yes, I am. Yeah, I'm still here.
Okay. So in that case, I'll still, since you already have your mic open, how about I still give you a question, yeah? But then I put the Corbin Cash hat, which is Ashley Martini's neighbor. I put that on for no good reason because.
I'm so sorry.
That's okay. So I watched your talk, and excellent, I must say. It was, of course, the least tribological talk because, of course, you did this before you joined a real tribology group with Ashley's group. But there's still several aspects in there that are definitely worth the while because, you know, it's materials, it's MDs, and I love MD. So I have one or two questions that I'd like to start you out with. So these first simulations that you talked about before you went into the experimental and the materials testing part of your talk, that was on Genite and that was non-reactive, right?
That's correct.
I'm not sure. Later on, you mentioned a compass force field. Was that compass, and you found out that this was not good enough for what you intended to do?
Yeah, that's correct. We initially worked with compass force field, and before I joined the group that I did this research with, they were all using compass force field. But I found that the properties were not properly calculated, and there were many limitations in the type of models that I needed to do, especially for these bi-layers or different layers models. It wouldn't have been the best force field in this case. And we also found that not just the bulk modulus wasn't good calculated for these cement-based phases that I showed in my presentation, but we also did analysis on some few more. And for those few more, it was even more, I'll not say worse, I'll say different from the expectation compared to experiments.
Okay,
So
because I mean, Compass is a standard, so it's not like you can't use it for anything. It was just that it came to its limitations, basically. And also, I mean, as soon as you're interested in some chemistry, that's where it ends. I mean, you can't use that anymore then. And just a second short one, because I have no idea how much detail you're going to go, but at the very end, in the Outlook, I think it was, you mentioned nanoparticles in the cement as additives to make their properties better, to make them safer, more sustainable, and so on. Was that any part of your thesis at all, or was that always an Outlook thing? Can you model that at all, or are there any force fields available?
Yeah, so it depends on the nanoparticle. So we use, my models were used to simulate later on silicon nanoparticles. Silicon is an important component in cement, and silicon nanoparticles are also used now. And what we found when we included them in the model is that the mechanical properties increase if the silicon nanoparticles were used up to 12%. Going above that, the mechanical properties in fact decrease. So that was the study that we did until I left that group for the Martini group, but there are still students working with Dr. Ram Mohan on that simulations, on that project.
So basically, you're not doing it anymore, but it is being pursued, and our bridges will continue to be safer.
Yeah, that's correct. That's correct.
Right. I have one or two more for you, but maybe later on, so we give the others a chance to talk as well. Okay. Thank you very much.
Thank you.
Yeah, maybe to continue with my old friend Manel. So Manel, we know each other already for many years, and of course it's a bit now half cheating that I try to figure out some new questions, but I have a couple of questions actually that might fit to the topic anyway. So you presented very nicely different kind of sulfides like MOS2 and WS2 and so on. And you know that we also have the discussion just recently about further compounds like molybdenum diselenide or ditelluride. What do you actually, from your personal experience over the last couple of years, what do you see as a kind of a tendency? Where does that all go to, and what would you expect, especially if you follow the line with the selenides and the tellurides? Do you expect something even more surprising or something much better performing, or what kind of potential do you actually see in that field?
Well, I think that from our observations, I think that the basic concept that we have, which is basically removing part of the job of the tribochemistry from the lubricant additives and putting into the material, this is something with a huge potential, and it will be probably required in the future as we are moving away from iron-based surfaces, and we are going towards the use of, or more extended use of lightweight materials such as aluminum, titanium, where you cannot use conventional additives, or also moving to coatings, PVD coatings, for example, nitride coatings or ceramic coatings, where you cannot expect to have these chemical reactions with conventional lubricant additives. I think that the concept itself, it have a huge future. From our observations, what we learned so far is that if you use pure molybdenum, which is like a very toy system, a model system, it works very, very well. We also learned that it works better with than with tungsten. Probably it's related to the formation or the stability of both compounds. So tungsten disulfide, it's known to be more stable, temperature stable. So probably it's also easier to form molybdenum disulfide. So I think that with molybdenum probably we have a easier way to go here. But still the challenges is as soon as you remove or you go away from pure molybdenum substrates so that you have lower molybdenum concentrations, then it's a bit more tricky to get this sustained friction. So there are still some open issues. So now we learn in our last 2-3 years of work which are the conditions that promote this tribochemical formation. So we learn that extreme pressures are beneficial, that high temperatures are beneficial. So we are narrowing down which are the conditions that are favorable, and I think that once we understand them, and it will be the basis for exploiting them using, for example, coatings, as we did briefly with Bernard Kohlhauser with these tungsten nitride coatings that I show. So probably with molybdenum base could we work even better, but still there are some open issues that are not fully known, which is the rate of formation, rate of removal. So sometimes it's a bit still tricky. So we noticed, for example, in the work of when Bernard was in Argonne National Lab, the experiments that he did there, that, for example, under some conditions, friction was very low, but the peaks of MOS2 in the Raman spectra were not so clear. And when you were to higher contact pressures, then you get more clear peaks in the Raman spectra, but the friction was higher, actually. So there is still some work to be done, actually, here.
Yeah, that's very interesting. I have another couple of questions, but we can also discuss that a little bit later about, let's say, potential of solid lubricants or layered materials in general regarding specific properties that are required for future applications. Maybe something that we can also discuss in the framework of other presentations that also half addressed or even fully addressed the topic of these kind of frictional layers. I'm thinking also of Arman, who will join us a little bit later today, but he also observed some stuff in these friction polymers. So I would like to maybe postpone my second and third question also when the other colleague is joining the session today.
Right. I mean, actually, we managed to talk to each of you, at least for a short time. And I mean, time flies. I'd like to give another short one to Ingrid, since she was the first one. She gets to, but maybe later on, I'm going to mix it up a little bit. Let's see how it goes. So let's move on to so first of all, it was very confusing because you used engineering notation. And if you're not an engineer like me, and if you and if C means carbon and S means sulfur and H means hydrogen, and suddenly you use those completely differently, it's a little confusing, but you can get used to it, I guess. So first of all, could you explain that a little bit to the other people here that haven't seen your talk yet, just briefly? And then I'd like you to tell us a little bit more about that interfacial, because that's as close to tribology as you got. You got an interface between what you called CSH and C3S, and one had water in it and the other didn't, and the water was sort of leaking into the other one. Can you expand a little bit more on that? How, let's say, what the exciting aspects of that are for you? That would be great.
Yeah, so we were studying cement-based, and in the civil engineering notation, they use different nomenclature. So C in this case is calcium oxide, it's not carbon. S is yeah, is silicon dioxide, and H, it relates to water. So you have CSH, that is a layer material that has all of these different components, like silicon dioxide, and then you have some water or OH components, and then the calcium layer, that is calcium oxide. So that will be CSH, and C3S is the same, tricalcium silicate. So you have also, it's also a layer material. And this was the most challenging part of the project, that is not your normal, I don't know, a metal that you have an FCC structure that is pretty constant. But in this case, modeling these very complex structures were more challenging than normally in MD. So we wanted to see the interface, as Stefan said, and what would be the effect. And we were very interested in see compression and see measure bulk modulus, but we were also interested in shear and define those properties. So in the talk, I talked just about compression, because what we saw was very interesting, that the water that was still part of one of these structures is a structural water, but when compressed, some of it was moving towards that layer where the interface was, and affecting the other layer, like hydrating. That is what happens when you mix dry cement or the powder that you're used to with water. So when that hydrates, the mechanical properties reduce, and the bulk modulus in this case reduce. So it wasn't a strict just a rule of mixture relationship in this case, that you have a certain amount of one component and another one of one component, and then you can determine the properties based on the ratio. In this case, what we saw is that one of those components was actually affecting the other one in a way that the mechanical properties and all the properties in general will change. So yeah, and the results that I show in the talk, you can see that the bulk modulus doesn't increase just linearly as you would expect, or like following rule of mixtures, but instead it just varies a lot.
Thank you. By the way, it just occurred to me, you're the only one that got away with the ice cream. I need to know if I get ice cream. Yeah.
Well, my favorite one would be ginger, but since it's so difficult to find, I will add to the chocolate trend, but it has to be dark chocolate, cannot be normal one.
But ginger rocks. Ginger would be great. I mean, sometimes I like ginger tea, so but real hot ginger. So last one for you, and actually it pertains to that last thing. So you had to actually get those two in the same system. You had to get the CSH and the C3S into one system, and they have a lattice mismatch. I think I talked with Gabriele Losi also about that at the last session, and that is a difficult thing. How did you go about that, and what were the trade-offs of having to match those lattices so you could pack the same pack those two materials in the same box, basically?
Yeah, it was very difficult. They are both triclinic, so it's not just the size what is different, but also they have different angles. So very, very different angles. So we had to create like a series of steps and rules that we will follow because it's not an established procedure. So the first one that we established was that we will use just to preserve the density of the system. That was an important one. We didn't want to go like away, make a huge box that will be completely unrealistic. So we used that as our initial volume. And then I created like a tiny algorithm just to find which sizes will be a good match. So to have the sizes and the angles matching, not completely, of course, I will never be able to find that, but in a way that I could increase one of the materials and match the other one, that let's say 2 to 3 or 2 to 4, and what would work better. So that was the second step. And then for the angles, we use just average of the angles. In this way, following all of this process, the mismatch with the actual calculated density was about 5% maximum, between 3 and 5, because we also had to take into account that because the structures are not, the borders are not next to each other, but there is an actual van der Waals force there, moving them, or like a repulsive one. This will add a little bit of van der Waals radius that needed to be added to the final volume and density of the structure. And then we allow for a very large equilibration of the volume following an MPT, keeping the number of atoms constant, but allowing the volume to change in controlling the pressure and temperature. So in that way also we allowed the systems to relax a little bit and take into account all of those repulsive forces that could occur.
So basically it's a matter of trying to get a system that's just not bad, not so bad that it just doesn't explode on you, sort of. And then you slowly ease it into a more comfortable position. It's like a massage thing, right?
Yeah, literally. Yeah. And I will say I try different methods, I try different forms, and this is why we have two different sets of models. One with the classical molecular dynamics, just bringing atoms into a box, and that's not very realistic at the end. And then we move into a more realistic that will be trying to create these layers, but do not go too far from it. That actually will happen. And actually that happens a lot of time at the beginning. I saw these weird behaviors with atoms moving all around. Yeah, that happened.
Well, thank you very much. That's all I have for now. It's been great having you. Of course, you're very welcome to still stay. But I'm going to pass it on to Carsten now.
So Manelito, una pregunta. Yeah, so we have a little question for Manel. You were working in the field of this diallyl disulfide, where you said in the presentation you can find that in garlic as well. Is that actually, I mean, of course, it's a natural substance, but is it to some amount, is it toxic? Is it very toxic? And how easy is that to get it extracted, actually? I was wondering that.
Well, the diallyl disulfide, one of the advantages is that it's environmentally friendly, as I mentioned in my presentation. It's a compound that is typically used as a food additive. So in principle, I mean, actually it's toxic, but it's toxic in very high concentrations. So probably the same is with garlic. So if you eat a high amount of garlic, probably will not be very good for your health. So diallyl disulfide, which is an extract of it, it could be toxic as well in big concentrations, but otherwise it's used as a food additive, so it's non-toxic in small amounts. And it's also interesting from the tribological point of view. It doesn't have any application technological, but from the tribological point of view, it's interesting because it's a disulfide, organic disulfide, very simple, so it has just a sulfur-sulfur bond and just a carbon chain at each side. So also for doing some model analysis could be also of very interest because it provides some simplicity to the system. But this was our idea was to use it as a environmental friendly additive to see if it's possible to build MOS2 with something that it's more friendly than ZEDP or conventional extreme pressure additives. In the case of the other mixture that we use in a different publication, there's a glycerol containing methionine. Methionine is an amino acid, sulfur containing amino acid. And in that particular case, glycerol is also used in some medical compounds and some recipes. So basically, that lubricant you could fully drink it without any problem. So you could drink that glycerol with methionine, and nothing bad should happen to you. And if you put it in the contact, you could build MOS2. So I think that's also very interesting.
Yeah, it is, as Paracelsus said a long time ago, right? It's about the dosage that makes the things a poison. When we talk about all these layered materials, Manel, and all the different coatings that we can use, I mean, for the solid lubrication, we know that most of the liquid lubricants, at least, and the greases, are one of the big advantages and tasks also for the application is, of course, to carry the heat away. So the cooling effect is even more important than the friction reduction for the lubricants. How is that from your perspective in terms of solid lubricants? What about the heat transfer or damping properties? If you substitute, let's say, a bearing that is typically grease lubricated by a raceway where we have a coating with a 2D material or layered material on top, how would you estimate that, or how is your opinion on that?
Well, I think that's a very challenging point, and that's something that maybe have deserved much less attention. So as you mentioned, everybody's mostly focused on reducing friction when you work with this kind of 2D materials, starting from DLC or graphene or MOS2. So most of the focus is laid down into having a very low friction. But what happens with the heat dissipation? That's a very critical question. And that's something that has not been studied from, at least that I know. So it's something that we were not taking into account. In our case, probably was not so important because we were still using a lubricant. So we were producing MOS2 tribochemically, but still we had a lubricated system. But in other work that we are doing using self-lubricating materials, where the material is self-lubricating by itself, without the need of an additional grease or oil. In that case, that's something very interesting and is something that could provide some concern. But on the other hand, these self-lubricating materials, sometimes they are meant to be used in cases where you typically use dry friction. So I think that in that case, maybe still it's a very big step compared to conventional metal-to-metal contacts. But in the case that you want to extend the use to other systems and to start making the concurrence to lubricants by using just self-lubricating materials, that's a point that should really be studied.
Yeah. Muchas gracias, amigo.